I'm in a ska band, the only one around. You can't hate me for a different sound. I don't care what you think of me, but maybe that's still too hard to see. So there's no place for us at all the clubs, because they just can't trust us to bring in the kids, see our shows. So no one ever goes. I'm upbeat now, even when I'm down. So don't give me that ugly, tired frown. You can't be sad when it's my job to make you smile. Try and take a walk in my McBees for a while.
Hey, we're back with more Ska Biology. I'm your host, Two-Tone Miles. As always, if you're watching this on YouTube, you should check us out at the WordPress site, scanbiology.wordpress.com. If you got questions about the material or want to talk ska, you can email me at scanbiology@gmail.com. So, on the intro track, we have Sorry We're Not Hardcore. It's by Uncle Joel's Comb off their full-length album, That Creepy Uncle, which was released in June of 2011. They're from New York. You can like them on Facebook, check them out on MySpace. They've got their whole album up on Bandcamp, so you can listen to it in its entirety for free, and then buy the tracks or the whole CD off Bandcamp. You can also get their music on iTunes. For the intro track, again, I selected Sorry We're Not Hardcore. This was a bit of a tough call. I was really digging Paul's Jam and Big Man on Campus, so it's tough to pick out the track I like the most. But I went with Sorry We're Not Hardcore, because this song's sort of a tongue-in-cheek apology for being a ska band in this day and age. And the joke being, with tracks this good, these guys have nothing to apologize about. Their CD's got some great stuff, so check out Uncle Joel's Comb. Stick around for the outro track. We got the Long Johns coming up. So, if you've been watching all my videos, then you know I've done some episodes kind of outside my usual Bio 101 type lectures. Talk about beer, bees, pizza, plant conservation. Basically just talking about things that I find interesting. So it's been a couple weeks since we've talked basic theory. So we're going to go back into some basic theory in this episode. Again, for the Bio 101 type lectures, I'm going to give them a formal episode number, this being episode 7. Whenever I just want to riff biology or talk ska, those vids, I'm not going to give them an episode number. Hope that's not too confusing. At any rate, I hope you get some clarity listening to the actual material, not by what I title the episodes. But like I said, this is the 7th numbered episode. We'll be talking enzymes here. So, we're getting really close to metabolism lectures. I know I keep teasing that and been saying that for about a month now. We've still got a few more basics to cover. The reason why I really am trying to set up metabolism as best I can is that's kind of where people run for the hills. That's where biology just kind of throws all its jargon at you in one fell swoop, and it can be real intimidating. So again, we're trying to cover basic theory here, so hopefully we don't scare you off. So before we get to metabolism, enzymes play a really important role in metabolism. So we really need to set up what is an enzyme. What do enzymes do? So enzymes are a class of proteins. We need to talk about what they do. Enzymes are catalysts. And if you take in chemistry, you may remember that a catalyst speeds up the reaction process. It's important to know that a catalyst does not get consumed or used up during the reaction process. So you start with an enzyme, it helps a chemical reaction to proceed, but at the end you get back still a fully functional enzyme. So basically an enzyme helps a reaction occur quickly, and then it goes back to its original state, where it can catalyze further reactions. So it basically just helps chemical processes occur quickly. And there are a lot of chemical processes within the cell that need to occur quickly. Neural signals, muscle contractions, these are things that need to happen very quickly, or else you could die as an organism. And so enzymes are real important in basically allowing the chemistry of life to proceed quickly so that life can exist and basically react in the moment, as it were. So now, in chemistry, there are two types of reactions that are important to consider here. An exergonic reaction converts the products to a low energy state and releases energy in the process. So if you're going to draw a curve of an exergonic reaction, you have kind of a high energy, little bit of a hump to get over, and then it drops you down to a low energy state. Whereas an endergonic process, you need energy to convert low energy reactants into high energy products. So that's kind of the reverse of the curve. You're starting down here at a low energy level. You've got kind of a big hill to climb. You get a little dip, and then you flatten out at a high energy level. So low energy reactants to high energy products. Now both type of reactions had kind of that little blip, that little energy hump. There needs to be some energy in the system to give it a boost, or else the reaction doesn't happen. Now in some cases, that energy hump is so large that the reaction, in the absence of the enzyme, in the absence of a catalyst, would be very, very rare. Now enzymes help to reduce that energy hump, meaning it takes less energy to get over the hump, and therefore the reaction occurs more easily, more frequently. So you can think of the energy hump without a catalyst basically being like a huge bump, whereas with a catalyst it's just a little blip. Now, if you go running or go biking, which is easier to climb, a big hill or just a little bump? I think we all know the answer. That's kind of what an enzyme does, is it takes that giant hill and reduces it down to a small bump so that it's a lot easier to do the chemical work of getting over that hump and converting reactants to products here. So let's try giving a real-world example here. Let's say you want a building demolished. So I suppose you could wait until the elements slowly erode the building away to nothing. And maybe even get lucky and a natural disaster takes it out. But this is going to require a lot of energy, a lot of time, and the energy is not particularly well directed. So that'd be the example of the reaction without a catalyst. It's going to take a lot of energy, and because it's going to take a lot of energy, waiting for it to occur naturally, it may take a long time for the energy conditions to be just right to bring down that building or break down those reactants into products. Now the reaction with a catalyst would be like taking a wrecking ball to the building. It happens much quicker than it would naturally, and the energy is more directed. A natural disaster may or may not take out the building you want. A wrecking ball, that is going to take out exactly what you want. So it's also done in a safe way to prevent harm to anything around it. Again, prevent harm to the biological system. Now let's say your building is so large you have to set demolition charges. You may need to set multiple charges and detonate them in a series. And this is kind of what an example of what a biochemical pathway is like, where you have to have multiple enzymes working in sequence, in concert, to basically break down one product into its reactant. So you got a multi-step process. You go from one enzyme to the next, to the next, to the next, to the next, and then finally you're at the end point. That's a pathway. So each charge basically would represent an individual enzyme, and they're all used in sequence to accomplish the task. In this case, our real-world example of bringing down a large building. So in the next lecture, that's going to be the glycolysis lecture, you're going to see how the simple act of splitting a glucose molecule, a sugar molecule, basically in half, is going to take no fewer than 10 enzymes to do this. Seems like a pretty simple thing, just Here's a molecule of sugar, cut it in half. 10 enzymes to do that. That's a biochemical pathway. And you can see how with 10 steps, there's going to be a lot of details. We're not going to go into all those details. We're going to talk just kind of surface level. Again, just not scare you away. Okay, so we're going to talk about the actual shape of enzymes. Now recall that we have all those amino acids to build enzymes with. So we have a lot of potential to make all sorts of different shapes. Each shape can be thought of as a different tool to do a different job, the job being the chemical reaction. Now the basic idea is that the enzymes have a little pocket that's called an active site, and that's where you bind the molecule or the substrate. So the enzyme binds the substrate, it's going to tweak it just a little bit and release the products. So you tweak both the enzyme and the substrate, and it gives it the chemical energy to carry out the reaction. Now once the reaction is complete, the enzyme is going to release the substrate and return to its original form. So the enzyme is ready to do this process all over again. Now a few more things to talk about here. Adenosine triphosphate, or ATP, can be considered the energy currency of the cell. Basically what ATP does is it takes a phosphate and it gives it to an enzyme and it becomes ADP. So you go from triphosphate, ATP, 3 phosphates, and you give a phosphate away, you become ADP with 2 phosphates, and giving that phosphate to the enzyme basically makes it, energized, ready to do the job. So again, many enzymes require a phosphate from ATP to work, and so activating and deactivating an enzyme occurs by adding or removing a phosphate. You consider this like hitting a chemical breaker switch. You have a phosphate hooked to the enzyme, it's in the on state, you take that phosphate off, it's in the off state. So many enzymes don't need to be doing chemical reactions all the time. They only need to do this when it's necessary. And so it's important to have those on-off mechanisms. There are also some ways to inhibit enzyme activity. So when you have competitive inhibition, that basically means you've got a molecule other than the substrate that's going to fit inside that active site and basically block the enzyme from binding the substrate, from doing its chemical reaction. The active site is blocked, and so nothing can get in, the chemical reaction doesn't occur. So it's called competitive inhibition because both the inhibitor and the substrate are competing for the same active site. Whereas in non-competitive inhibition, the inhibitor doesn't bind the active site. It's going to bind somewhere else. But when the inhibitor binds, it causes the whole enzyme to fold in a way that's going to block the active site. So it's like, if this were my active site, we're going to bind an inhibitor down here at, say, the wrist, and suddenly the enzyme folds. I no longer have an active site. So this example of non-competitive inhibition brings us around to allosteric interactions. Okay, so this is going to be a bit complicated. Hopefully I can do a good job talking this and we can get through this. Allosteric is from the Greek words allos, which means other, and stereos, which means object. It basically means that by binding something at an area other than the active site, so in non-competitive inhibition, you're binding an area other than the active site. This is an example of an allosteric interaction. You're binding something other than the active site, that's allosteric. But not all allosteric interactions are about inhibition. In some cases, binding something at an allosteric site is needed to convert the protein to an on form. So allosteric can go both ways. It can turn the protein off, or it can turn the protein on, depending on what's binding and where. Alright, this is going to be the last concept to cover for this lecture, feedback inhibition. Now, feedback inhibition plays into biological pathways. Let's say you're breaking down sugar to feed your muscles during exercise. Now, say you stop exercising. Suddenly, the products of breaking down sugar, they're starting to build up. And there's really no reason to keep breaking down sugar. You're no longer exercising, your muscles are basically well-fed at this point. So you don't need to keep breaking down sugar, and you like to turn the pathway off, or maybe even reverse it. You have all those sugar breakdown products, and we're done exercising. Let's take those products and build them back into sugar, or maybe into something else. So in feedback inhibition, basically a later step of the pathway goes back and regulates an early step of the pathway. So this would be like if you, let's say you got a 7-step pathway. Basically, you know, your products from steps, say step 6, once they start to build up, it says, oh, hey, go back here, stop step 1, stop step 1, stop the pathway, we're good, we've got too much of whatever it is as it is. So we'll go back to our factory metaphor. I introduced this in a couple of the earlier lectures. So let's say you're packing up orders for shipment, and suddenly you've met all your orders. But the folks working on the line, they don't know this. They're still building product. So you send a guy off the packing line to the earlier steps in production and tell them, you know, we've packed up all our orders. We're done. Stop building product. And so you send a guy and he says, okay, shut down the upstream production machinery. We've met our orders. We're done with the order. So that act of saying, okay, that's enough, stop building product in the context of a biological pathway, that's what feedback inhibition is all about. So I hope this hasn't been too confusing. It's been a while since I've done kind of basic biological theory, so if I'm a little rusty, I apologize for that. Again, if you got questions on the material, hit me up with an email. Again, scottandbiology@gmail.com. I'm Two-Tone Miles. I hope you learned something. And on the outro track, we've got Hurting by the Long Johns. They're out of Tampa, Florida. They've opened for Mustard Plug, Big D, a lot of other great bands. I got this track Hurting as a free download off their Facebook page, and they've got more tracks available for download. Do yourself a favor, like this band on Facebook, download the tracks, spread the word. This is a band that's got some great energy, an amazing lead vocalist. So yeah, you're definitely going to want to check out the long track.